Thank you, Gwen, for the recording. The agenda and the speakers. Today, I will start with a short presentation on the interTwin project, an introduction. I am Charis Chatzykyriakou, by the way. I work as a project manager at the Earth Observation Data Center in Vienna, Austria. And then we will have 4 presentations on specific environmental use cases from the interTwin project. We will start with Donatello Elia. He's going to present the digital twins for projecting the occurrence of tropical cyclones and wildfire dangers due to climate change. And Donatello is a computer scientist at the Advanced Scientific Computing Division of CMC Foundation in Italy. Let me just fix my screen a bit because I'm blocked. Okay. We will continue with Christian Pagé from CERFACS. He's going to present the extreme rainfall, temperature, and wind weather event changes in response to climate change. Christian is a research engineer and project manager in climate science in CERFACS in Toulouse, France. Björn Backeberg will continue. He will present us the digital twins for flood early warning and flood impact modeling in coastal and inland regions. Björn is the senior researcher and project leader in the hydrodynamics and forecasting department of Deltares in the Netherlands. And Iacopo Ferrario will finish with a presentation on a digital twin for drought early warning in the Alps. Iacopo is a researcher in hybrid modeling and Earth observation applications in hydrology at EURAC in Italy as well. And with no further delay, I would like to start with the first presentation, which is the introduction to the project, as promised. And I would like to go directly to the main objective of interTwin, which is the co-design and implementation of the prototype of an interdisciplinary digital twin engine. Let me call it DTE from now on to save time. interTwin is going to develop the digital twin engine, and is actually already developing it as an open source platform and based on open standards. The co-design is happening with the help of a large spectrum of use cases from 2 broad scientific domains, the one of physics and the one of environment. As you can see on the scheme on the right, the approach that we follow in the project is based on defining the design and the specification for DTE and the software modules, releasing the software modules, then the integration activities follow, and the validation. And this circle will happen around 3 times in the project. You will see later the timeline. A few words on the consortium and the project. So the project started in 1st of September in 2022, and it's going to last for 3 years. The budget is approximately 12 million euros. And there is a pan-European coverage of partners, as you can see in the map. The project is coordinated by EGI, the EGI Foundation, and there are 32 more partners, of which 10 are resource providers, and they provide cloud, HPC, and HTC resources. We have 11 technology providers who deliver DTE infrastructure and horizontal capabilities. And there are also 14 partners that represent specific scientific communities from 5 domains. The timeline that I promised. So as you can see, the project is split into 3 years. And now we are at a bit after the half of the 2nd year. During the 1st year, the first version of the design and specification, as well as the blueprint architecture were published, and the digital twin applications design as well. In the beginning of the 2nd year, the first version of the software releases happened, and the 2nd version of the blueprint architecture. Right now, the project focuses on the validation of the DT applications, and the design, the 2nd version of the design and specifications is going to follow later in the year. Finally, in project year 3, there's going to be the 3rd and final version of the blueprint architecture, and there's going to be the 2nd and final versions of the software releases and the validation of the DT applications. The components of the DTE, of the digital twin engine, are the ones that you see in this slide. So starting from the bottom and going up, we have the DTE infrastructure, which consists of hardware and software. When it comes to the hardware, there are HTC, HPC, and cloud resources, as mentioned before, but also data repositories. When it comes to the software, we have the orchestrator and federated data management. Then we have the DTE core modules, and we are developing specific core modules for quality verification, for workflow composition, and real-time acquisition and processing. Then we have the DTE thematic modules, which are specialized for specific scientific communities. You see the environmental sciences, physics domains, specific physics domains, and hopefully in the future we're gonna work with more scientific fields. And on top of that, we have the DT applications, which are implemented through the use cases, and they are the tool for the co-design, let's say. It's worth mentioning that there are going to be specialized webinars for these core modules and the thematic modules in the future, so stay tuned for that. Going now to the use cases, as we mentioned, there are use cases from the environment domain and from the physics domain. In this slide, you can see the specific, like the subdomains, the specific domains, and the partners that implement them. Starting with the environment, since it's also the topic of today's webinar, we have the tropical cyclone detection. I'm not going to mention the partners just for the sake of time, but you can have a look at them. The early warning for extreme events, the wildfire hazard map generation, and the extreme events impact. And then when it comes to the physics domain, we have radio astronomy, lattice QCD, gravitational wave, and high energy physics. A note on the benefits of the interdisciplinary approach, which interTwin follows. First of all, it increases the cross-community development efforts, and it helps breaking down the silos, as we say. In addition, it contributes to infrastructure agnostic DT workflows that can run across multiple HPC centers. It makes the extensibility, so the addition of new use cases easier, but as well as the modularity, so to customize the workflows for specific needs, for specific use case needs. Also worth mentioning is our collaboration with the Destination Earth under interTwin, with the main goal the interoperability. So interTwin is having joint activities with Destination Earth to design a compatible architecture and interoperable architecture that will satisfy the needs of larger set of user communities. They develop common software architecture concepts that are also applicable to other major DT initiatives that are happening right now in Europe. And two last slides on important results that you might be interested in. So the second version of the blueprint architecture and design specifications are already available and accessible in GitHub and in Zenodo. You can follow the links and have a look at them. And the first release of the software components are also published in the interTwin website. There are 38 components in total, and these are core DTE modules, infrastructure modules, thematic modules for the environment and for physics. And you can find also the workflows, so the open source material under the interTwin community on GitHub. So we invite you to explore those too. And with this, I would like to hand over to our first use case lead, which is Donatello Elia. And Donatello, the floor is yours. Please let me know when you want to join the slide.
Okay. Good afternoon, everyone. Thank you, Charis, introduction. So I'll present the work that our team from the EURAC Center of Climate Change together with the University of Trento in Italy and the Institute Pierre Simon Laplace in France, is carrying out in the interTwin project. And this is related, as Charis mentioned, to the development of digital twin application on extreme weather events. And in particular, we're focusing on tropical cyclones and wildfires. Next slide, please. So just a bit of motivation behind this work. So the increase in global temperatures is leading to an aggravation of extreme weather and climate events, including storm and wildfires. And such events, of course, can pose a significant threat to people lives and the human activities. So, for example, tropical cyclone, which is one of the most destructive weather phenomena, their intensity and frequency is expected to increase due to climate change. And also for wildfires, for example, 2023 was the warmest year on record and had an unprecedented scale of wildfires globally. So it's clear that analyzing the impact of climate change on such extreme weather events is a very important task. Next slide, please. Okay, thank you. So traditional approach for predicting and detecting such events are usually based on deterministic solutions, and they rely, for example, on threshold-based algorithms or make use of heuristics. But nowadays we have huge amounts of data. So the goal was, let's try to understand if we can take advantage of this big amount of data for extracting knowledge using some data-driven approach. So we are exploiting machine learning to basically learn the patterns associated with extreme weather events on past data. And then we use these trained models, applying them on future projection data for the detection and prediction of such extreme events. So these data-driven models have the advantage of being cost-effective, of course, after the training stage, which can be quite time-consuming, and can also be kind of generalizable to different geographical areas. Next slide, please. Of course, such solution carry also some challenges due to the big amount of data that needs to be handled, and also the computational aspects for the training. As is quite well known in data-driven application, a lot of the effort has to be put on the data preparation stage. So even before doing the training of the model, we need to gather the data, select the proper data, prepare this data in order to be fed to the model. So this part is quite important. Also, training and preprocessing can be quite compute intensive, with the need, for example, of GPUs and HPC infrastructure for scaling the training and make it faster. And then the overall workflow for training these models can become quite complex. So being able to automate it can help to speed up the process, for example, in hyper parameter tuning, and support also the reproducibility of the results. Next slide, please. So in our work in the interTwin project, we're exploring these machine learning models together with a set of past data from multiple sources and the climate projection data as key components for this digital twin application on extreme weather events. In particular, we're targeting, as mentioned, tropical cyclones and wildfire. So such digital twin application will provide basically scientists and the user in general, let's say, with a tool for analyzing these events according, for example, to a given climate projection scenario. So they, for example, can run some what-if analysis. And although, as mentioned, the learning stage of the model can be slow, once it's trained, the models are quite fast. So this can in general kind of speed up the generation of the results. And on the same line, we are targeting the use of graphical interface based on Jupyter notebooks to provide an effective tool to simplify basically the process. This can be used both from developers' point of view, which are interested maybe in doing some tuning of these data-driven models, but also from the end user, which are basically interesting on kind of visualizing the output. And this implementation is done by exploiting the interTwin digital twin engine, which was presented by Charis in the previous presentation. And basically, this provides the framework for the implementation of such type of use cases. Next slide, please. So the first use case we are working on is the one on tropical cyclones. And basically here the goal is to try to detect and locate the tropical cyclone centers. And here we're using convolutional neural networks. What we're looking for here is basically to understand the trend in the frequency and the location of the tropical cycles according to climate change. So for the model training, we're relying on a set of variables like, for example, wind gas, temperature, sea level pressure, which we're gathering from the EURAC global reanalysis dataset from the ECMWF. And these are used as predictors for the tropical cyclones. And then we're using the EBTracks database, which contains a set of historical tracks and the position of the actual tropical cyclones that happen. And this is used as target of the model. So we try to basically link together some input variables and the target, and then the model will try to understand the pattern that basically leads to this to the tropical cycle. And to this end, we have evaluated different configuration of the convolutional neural network models, in particular in terms of hyperparameters like the loss function, but also in terms of the structure of the model. And we have basically implemented a machine learning ensemble approach, and this approach aims to improve the localization skill of the single machine learning model. So the basic idea is that we try to join together the capabilities of the single trained models by averaging together their results, with the goal basically to improve the localization of the tropical cyclone sensor, providing better localization than the single model could do. Anyway, if you're interested, more details are available in the paper linked at the end of the slide. In the context of the project, besides the convolutional neural network, we're also investigating other machine learning approaches, for example, those based on graph networks, which were being evaluated by a team at the University of Trento. And these different approaches are being integrated into one of the interTwin thematic modules, which is linked to this to the management of tropical cyclone detection. At the current stage, we have a first set of models which have been trained and validated, and now we're working on the initial evaluation of such machine learning models on climate data projection, in particular from CMIP6. First of all, are interesting, but of course we need to investigate them a bit better in order to understand the results. However, the tropical cyclone have some consistent patterns, so that's good. Next slide, please. Then the second application we're working on is the one on wildfires, and basically this digital twin application aims to generate wildfire danger maps, and more specifically, it aims to predict the barred areas. And also in this case, we are exploiting convolutional neural network using the UNet++, which is a state-of-the-art model. This application is a bit in an earlier stage than the previous one. We're still conducting some validation. Anyway, the goal is to provide basically an end-to-end approach for the generation of these wildfire danger maps, which aim to give an indication on the temporal and geographical trend of the wildfire, as well as the potential extent of wildfires when they in the case these are predicted. We have been evaluating different configurations also in this case, and also conducted a sort of correlation analysis to understand which variables are more correlated with the barred area. For the training, we're using in this case the CERFACS, which is a dataset which basically provides a harmonized dataset integrating both weather and Earth observation variables. Next slide, please. So the workflows for use cases are in both cases quite complex. The slide just shows a high-level view of the inference pipeline for tropical cyclone use case, but the one for wildfires is quite similar. Just different blocks on in the green part. So the digital twin engine of the interTwin project design is providing the components to support the implementation. In particular, for example, we can select in the blue box the data lake. It provides the support to access different type of climate and weather data. And this can be accessed by the data lake. We're also trying to understand the use of catalogs to access environmental data. So this can be this can allow simplification of data, basically data access and selection of the proper variables. And the project also enables the usage of different infrastructure transparently. So when running the workflow, we don't need to basically interact directly with the infrastructure. And then another important point is the project is also providing the workflow management capability so that we can run different steps of the workflow in a automated manner, and then also track the provenance through these tools. Next slide. This is just an overview of the work. At the current stage, we are kind of midway through the project. So we are currently working on the integration of the different components with the digital twin engine, and we're also working, of course, on further improvements and validation of the machine learning models. And as mentioned, we expect to make this application available to end users through Jupyter notebooks. And one of the main points we're now working is related to the evaluation of the results on climate projection data. And I guess that ends my presentation. I'll pass the stage back to Charis. Thank you.
Thank you very much, Donatello. We continue directly with Christian Pagé for the extreme rainfall, temperature, and wind weather event changes.
Thank you, Charis, for the introduction. So what I will present you is also a digital twin. And so myself, Christian Pagé, and Andrew has been developing this application. So next slide. So the challenge is also in climatic streams. So there are many things that are in common with the use case that have been presented by Donatello. So the generic, what we aim at is to have an application, digital twin application, that implements the general detection algorithm for climatic streams. So you can think of intense rainfall, drought, heat wave, cold spell, high wind, and also others. And what we want to do is to characterize, to be able to do what-if scenarios. So the characteristics of climatic streams that we want to extract are the frequency of occurrence, so and also the spatial extent of those extreme events, the intensity. It can be relevant or not depending on the specific climatic streams, and also their duration. And we have to be aware that for those climatic extreme events, there are different categories. There are some that are one-time events, so for example, happening on one day. And there are other extremes that are extremes because they last for some time. And so we can see that there's a difference between a day with intense rainfall and high wind, which will be very short in time, and also longer term events like droughts that can last for weeks, even months. So those two kinds of climatic streams will be addressed with this method. Next slide, please. And so the challenge related to climatic streams, we have seen recently a lot of weather extreme events, and those are happening all around the world, and also more frequently, more intense, and they have more impacts. So we can see a change in how the weather extreme events are happening right now. So there's a really urgent need for the impact assessments to know what will be the situation in the next decades. We do that because we need to identify mitigation solutions. Sometimes those solutions can take time to be implemented. It's not straightforward, and there are maybe many solutions possible, and some involve a lot of funding. So there's a need to really plan in advance. It's also possible to do extreme events attribution. And all of this affect multiple domains. We can think of infrastructures, urban areas, agriculture, transportation, food security, and tourism. There are many domains that are impacted by those climatic streams. So, and we need flexible tools to unlock all the data we have for the future climate simulations. They are not really straightforward to use for end users. So the goal here is to build tools that are very useful for end user applications. Next slide, please. So to evaluate climate exchange, we can calculate climate indices and indicators. And here we can group them among different parameters. For example, you can have temperature indices for heat and cold. You can have wind indices. You can also have climate indices related to precipitation, rain, snow, or drought. And also have some related to humidity and wind. And you can also combine them. For example, if you have two types of atmospheric parameters that are important for an extreme. For example, you can have wind and rain, and there will be more impact because of that, because rain will make trees more vulnerable to high wind. So this is one example. And also temperature, if you have heat and humidity at the same time, it's also the case. So compound indices. So we have a package called iClim to do that. But the thing is that it works quite well. What is standard analytics, and it takes a lot of complete time to generate those climate indices and indicators. So we are looking at more performance in calculating those. Next slide, please. So this is the high-level workflow from a user perspective. So the user is on the left-hand side, so interacting with the digital twin application using Jupyter notebooks. So in the workflow, the user will first select which climate simulation he wants to use. And from this selection, it can depend on the greenhouse gas scenarios the user is interested in, or how many climate models, and also which time period. So from this information, there will be subsetting and pre-processing being done. And then all this data would be handed to the extreme event characterization digital twin application. So this will be done per climate model. So for each climate model, this process will take place. And this workflow will be repeated for each climate model to have a more possibilities to see what kind of scenarios would be possible in the future. And from this output, we generate statistics and we post-process the data for the end user and generate specific products on demand. Next slide, please. So why we use a artificial intelligence-based method? So I told you a little bit about it. So it's really to analyze a very large database of climate scenarios with sufficient performance, and also to make use of the new architectures like GPUs that are less, that use less energy and that are faster. So, and also sometimes some computers have a lot of GPUs, but not so many CPUs. So it's a good addition. It's also scalable in cloud-based environments. And the idea came first because they use this kind of artificial intelligence method to detect avalanche in satellite images. And the method used was a variational autoencoder. So it's a deep learning technique. And this is that kind of technique we also use in this use case. Next slide, please. So the method itself, more precisely, is the convolutional variational autoencoder. And to explain it in very simple words, you have an input to the left-hand side image. So we have a 2D field of one parameter. It can be, for example, temperature, surface temperature. And then you go to a convolutional neural network. And then you go into a space which has less dimension. So the idea here is that it's like loss compression. In fact, you lose some of the information, but you keep the most important one. And then you reconstruct the image after that. This space is called the latent space. So you have encoder, latent space with the most important features being kept, and the decoder. So then when you reconstruct the image, you can train your model over several years, and then the model will adjust itself, but there will be some reconstruction error for some of the days. Why? Because we have weather extremes event happening, and so this is very short in time and in space, so it will not be captured by the lower dimension space. And this is what we are interested in. So we use this error to detect the climate extremes themselves and then characterize them with frequency, duration, and intensity. So this package is open source, so it's still alpha. It's called XTClim, and it's available free as well. Next slide, please. So what kind of data we are using? We are also using CMIP6 data, so we share common data set with the previous use case. This is an example using one model, CMCC SM2, but it can be any other one. So we use a coarse grid, but we can also apply this method using higher resolution climate simulation as well. We use the long data set, and then for now we use temperature, but we can use this method for other variables like precipitation and wind, and we apply it to various carbon emission scenarios. So the pre-processing, so it's a NetCDF is a file format, so all this data is stored in this file format that is standard, and then we use a square over Western Europe, and we split by season, and then we pre-process the data so it is usable by the method itself. So this could be applied in other parts of the world. It's just that for the first test of the model, we ran it over Europe, but it could be over other regions as well. Next slide, please. So those are the first results. This is what we were expecting. Here we compare different greenhouse gas scenarios in different colors. So what you can retain is that on the upper right, you see the greenhouse gas concentration increasing in different scenarios, more in the violet scenario than the green one. And then on the left-hand side, you see the error in reconstruction. So it's related to the climate extremes, as I explained. And you see that when you have more concentration in CO2 in those scenarios, you have more climate extremes. So this is what we expect, and this is also what we can see when we calculate this analytically. Next slide, please. And we can also compare use only one climate model, but different realization. So different simulation for the same climate model, and then we can do ensemble member analysis. So we have let's say 30 or 50 simulations of the same model, and then we have some uncertainty because of the climate system. Next slide. So the perspective is to exploit the geospatial information to extract the spatial coverage of each extreme. The implementation of a severity index to better compare events. So we want to exploit more the lower dimensional space. We will also validate this with the analytical method. And then the integration with the interTwin architecture and components is going on right now. And we want to extend that to other climate variables as well. Next slide. And so what you can retain of this use case and presentation is that we use artificial intelligence method called variational autoencoder. So it is an anomaly detection method. It can handle big data of high complexity, and we characterize the extreme events using various indicators, and the results are consistent with what we are expecting. And so all of this enables end users to better quantify the climate impact uncertainties given different scenarios. So thank you for your attention.
Thank you very much, Christian, for this presentation. The next one is Björn Backeberg, if you're ready, on the floods. The floor is yours.
Thank you very much, Charis. So my name is Björn. I'll be representing the Deltares team working on the interTwin use case for digital twins on flood early warning and flood modeling in coastal and inland regions. Next slide, please. So the objectives for this use case are twofold. One is to enable expert users or digital twin builders to easily set up digital twins for flood early warning and climate impact assessment using the digital twin engine that's coming out of interTwin. And the second is that these digital twins then empower communities to make informed flood risk management and adaptation plans, taking into consideration a range of risk drivers. For example, sea level rise or changes in storm frequency or changes in precipitation patterns. But also risk drivers are related to socioeconomic changes such as population growth and economic growth. All of these influence how risk evolves as we move into the future. And the question that we need to understand for adaptation planning is that what is the system response to all of these changes? Not only in response to the drivers, but also in response to the actions that we take to mitigate against these risks. Next slide, please. So our starting, so to understand these system responses requires modeling, which is often a bottleneck for adaptation planners. And the idea here is that we make modeling faster, easier, and more accessible to people that need the information. So our starting point for this work here is an application that we developed at Deltares called FloodAdapt, which I'm going to run you through quickly. So next slide, please. So I'm going to quickly walk you through what FloodAdapt does. FloodAdapt is centered around the kinds of questions that people ask when they do adaptation planning. So here you see a couple of examples. For example, people ask questions about population growth, what would happen to risk in terms of population if the population doubles, or how long is a drainage pump effective in the case of floods, or what would have happened if a storm track would have been further south. Next slide, please. So these types of questions can then be translated into modeling inputs, which is what FloodAdapt does. And this is done by specifying 3 components. And these components are then basically what we term what-if scenarios, and include like projections about the future change, for example, sea level rise or population growth, or you could specify an event, which could be either historic or synthetic. And then you can also specify strategies, which are combinations of measures that you can take to try and mitigate the risks and impacts. Next slide, please. So then once the scenario components are specified, they get sent to a backend. Slide. And then this backend is connected to a hazard model and a damage model. Next and next. And at the moment, these are connected to two models. On the left, you see Sphinx, which is a reduced physics-based flood inundation model. And on the right-hand side, it's the flood impact assessment tool, which calculates damages. And then as you specify your scenarios, the backend then changes the models to take into account the changes that the scenario changes that you want to model. For example, if you want to specify a flood wall, you need to make changes to the underpinning Sphinx model. And the backend does that automatically. So you as the expert user, you don't have to go into the model code to make the changes to the model. Next slide. The backend then runs the models and produces outputs that is accessible to end users. So easy to understand metrics or spatial maps. So we provide infographics and infometrics to help users understand what the scenario impact was that they've just modeled. So next slide. I'm going to give you a quick example of a community question. For example, here we have the example of Hurricane Ian, and we wanted to ask the question, what would have happened if Hurricane Ian made landfall further south? Next slide. And click next. So here you see the desktop application, that's probably important to note, of FloodAdapt, where users can click through and select events. And what you see the user doing here is he selected Hurricane Ian from the database of hurricane tracks. And here you see a whole bunch of information about the hurricane itself, where it made landfall. You can see information about its intensity. If you hover over the little image, you see the wind speeds associated with that current position. And there in the middle, you see sort of Charleston, which was our use case for this specific example. And then we can also move the hurricane track 25 miles to the east in this case. In this example, we shifted to 70 miles to the east to make landfall further south. We give it a name, and then we have our scenario, and then we run that example. Next slide, please. Then when you run those two simulations, on the left-hand side, you see the original Hurricane Ian flood inundation map. On the right-hand side, you see the simulated output of what would have happened if the hurricane would have made landfall further south. You can also calculate the damages, and you can see that you can compare in this what-if scenario the amount of damages to buildings that would have happened in this if the hurricane was made landfall further south. As you zoom in, you can see more details, and you can zoom down to sort of building level detail. Next slide. So, and then finally, what we also do is we provide sort of summary infographics or summary information to help people sort of give an overview of what the response was, or what the what-if scenario, what happened essentially. So here we summarize the information in terms of building damage. We categorize it into different categories like homes, businesses, and we can give you information about whether or not there was minor, major, or destructive damage. We can also provide information about the people, how many of them were affected by the floods, or how many of them were even displaced by the flooding. Next slide. So here, as I mentioned, FloodAdapt is a desktop application. So in the next couple of slides, I just want to present the work that we're doing to transition FloodAdapt to a web application leveraging the digital twin engine. And we are also expanding the types of models that you can use with FloodAdapt. I mentioned Sphinx and Fiat, but we're expanding those capabilities, and we're also building tools that allows users to deploy these models anywhere on Earth. So what you see here in this slide is a high-level overview of the workflow. So on the left-hand side, you would start on the left where the user can define sort of a region of interest or other sort of parameters that are necessary for the model. And then we have our HydroMT model builder, which then sets up the Sphinx and WFlow models. Click next and next, which is our flood inundation and our hydrological model. These then are triggered and run to produce flood maps. And we are working with the Technical University of Vienna and EURAC, the EODC, my apologies, to incorporate the global flood monitor as an additional input source for flood mapping. Next, these flood maps are then handed over to Fiat, which uses them as input to calculate the damages to buildings. And then next, and then the additional feature that we're adding in interTwin is RACE, which is another model that can calculate impact on accessibility. So for example, if a flood occurs, this model can highlight which communities are isolated and have difficulty accessing hospitals, for example. Next slide. And next. So just to give you a brief overview of where we are with our developments, this is, sorry for this complicated slide, but central to it, kind of in the middle on the left, is this Jupyter Notebook, which is our main interface for engaging with these models. So a user will be able to set up models, the different models that I was speaking about. Then they will be able to set up a site and configure scenarios. And then once that is done, they can basically call workflows to run the models that are needed for those scenarios. The models are then automatically pre-processed and run in the correct order. And then all of the data is then written to the data lake, which is the integration with the digital twin engine work that we're doing as well. And then from the data lake, we read the information back and then visualize the output. And here we're basically porting the information from the FloodAdapt desktop application to the Jupyter Notebook and making that all available. If you can click next, 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 and next, and next. This is kind of the work that is in progress. So as I was mentioning, we're working on the improvements to setting up the site and configuring the scenario, making that as easy as possible for an expert user still. So somebody that's familiar with Python and can work with Jupyter Notebooks. We're working on the workflows at the moment, in particular to building on using the common workflow language as our main interface in interTwin. And then we're working on capabilities to read and write from the data lake that's being developed in interTwin. Then next. One more time. Thank you. So these are the work that we're doing in terms of the different models. So we are adding RACE to the workflow, which I mentioned before. For Sphinx, we're building a workflow to also do probabilistic flood maps. So at the moment, we predominantly work with deterministic flood maps. Probabilistic flood maps will give you an indication of risk and return periods. Then we're also working on green infrastructure options as mitigation measures for flooding. We will also be providing examples of using local data, because typically at the moment we use global data, which is generally a little bit less accurate than, for example, local LiDAR surveys to get digital elevation models at a high resolution. We're also improving our downscaling and validation methods for Sphinx. And then finally, for Fiat, we're building Docker containers and also giving examples of how to use local input. For WFlow, which is our hydrological model, we're working on improving how to quantify the nature-based solutions in terms of mitigation measures for flooding. Next slide. Then finally, as an output of this project, we're working towards 2 demonstrators. The first one will be a flood early warning system demonstrated for Humber in the UK. This one will rely on Sphinx and WFlow, and effectively what we're doing is we're taking demonstrator operational weather forecasts and just demonstrating that we can run a system operationally and produce, for example, 5-day forecasts every day, and then trigger early warnings should a flood be detected. And in the second use case is essentially the same, but we're working more with the sort of what I demonstrated with Flood Adapt, combining Fiat and Race to calculate damages for different scenarios. Next slide. And that was it for me. Thank you very much.
Thank you very much. I was really entertained with the next. And we're going to the next and final speaker, Iacopo.
Good afternoon.
Good afternoon. Who's going to present us his use case about the droughts, and the floor is yours, Iacopo.
Yes, thank you. So yeah, I'm going to present the use case on the digital twin for drought early warning systems in the Alps. And therefore, I will introduce briefly the challenge that motivated the proposed use case before diving into more technical details. Yes, in general terms, droughts can be defined as periods with a deficit of water compared to normal conditions. And behind this apparent simplicity, the droughts are very complex phenomena with multifaceted characteristics. The temporal development of drought is marked by an onset, a persistence, and finally a termination. And after termination, there is this period of recovery where the system may or may not return to previous condition. The magnitude of drought is described by the intensity, the duration, and severity. And finally, a crucial process is the propagation of the meteorological anomaly to the different land component of the water cycle that eventually generate the so-called agricultural and hydrological drought. So in the last 50 years, in the Alpine region, drought seasonality and the relative frequency of drought generating processes have changed substantially. And as well, looking ahead toward the future, climate projections show clear trends in terms of increasing temperature and shifting precipitation pattern, meaning less water in summer and more water in winter, but less snow, more rainfall. That can further exacerbate the ongoing changes. Next slide, please. Drought can have profound impacts on ecological and socioeconomic system. For example, drought can reduce the vitality of trees, increasing their mortality and increasing the probability of outbreak of parasites. Then it can increase the probability of wildfire, can lead to restriction in public water supply and reduction in productivity of crops. A study by Stefan in 2021 highlighted that in the Alpine region, the most impacted sector, ordered by number of reported impacts, were agriculture and livestock, public water supply, forestry, and hydroelectric power generation. Next slide. So early warning systems, therefore, are proven and effective climate adaptation measure for addressing climate hazard. And the digital twin that I'm presenting aims at prototyping a system that provides monitoring, modeling, and forecasting capabilities. We identified 3 potential type of users of the system. Each of them have different data and information needs, the technical skill, and different objective. For example, a researcher may be interested in studying compound impacts of droughts, testing different input dataset by performing data fusions, or trying different modeling hydrological models. Then water agency may need water availability forecasts for the next months from informing municipalities and plan preventive actions. And journalists may want to report drought condition in the Alpine region for informing the general public. Therefore, the system that we propose should have the following characteristic. You should have customizable processing workflow and access to cloud computing resources and machine learning modules. And you then have access to Earth observation, climate and geological data, and provide the possibility to estimate uncertainty, and finally to a visualization interface to visualize the output. So in that sense, the system should take the meteorological seasonal forecast from ECWFC's 5 system. They are initialized every month, and they provide meteorological forecasts for the next 6 months at a daily resolution. These are fed into a modeling workflow. That's the domain of this model is modeling workflow is the Alpine region, and we identified 25 basins, and it's modeled at 1 kilometer resolution and a daily time scale. The output of the modeling workflow are 3 hydrological variables, in this case, evapotranspiration, surface soil moisture, and stream flow, from which then we basically compute drought indices. Next slide. Talking more about the modeling workflow and modeling approach. So we decided to adopt a hybrid modeling approach, which combined the strengths of physical-based and data-driven model. That so these desirable properties such as faster computation. We're talking about seconds versus hours, or so 10 times 1,000 times faster, which lead to faster predictions and the possibility to do sensitivity analysis, for example. Then maintaining interpretability, which is crucial for decision making, handling heterogeneous and potentially massive data inputs, the possibility to perform data-driven knowledge discovery, the composability of the architecture and the flexibility, and finally to perform a data simulation to improve model accuracy. So on the right, you can see the 3 main components of the workflow. The first one is the one highlighted in red, is the one that we actually have developed for this release, and is the pretrain of the surrogate model, where physical knowledge from the hydrological Tableflow model is injected into the deep learning model, which is an LSTM, by minimizing the loss function between the Tableflow model output and the surrogate output. The input of the surrogate model are forcing variable and Tableflow static parameter. These are the parameter, are conceptual physical parameters that are not observable and are identified by calibration. When the surrogate is trained, we freeze the weights of the surrogate and use it in the parameter learning application on the right. The goal of this application is to find the best set of Tableflow parameter, which are the input of the surrogate, that minimize the loss function between the variables simulated by the surrogate and observation from remote sensing and in situ stream flow stations. The parameters are optimized by plugging a neural network architecture, which is the one which is the box in purple, so is the purple box, that learns a transfer and upscaling mapping from catchment attributes and such as soil properties, topography, vegetation phenology and structure, and so on. And the parameter of and the static parameter of Tableflow, and this also allows for knowledge discovery thanks to additional techniques such as symbolic regression. Finally, the last application is the one that produced the hydrological variable. Next slide. So there is a quite diverse amount of data that are needed by this modeling workflow. And produced by the different components. So the hydrological model needs forcings from reanalysis and of course CS5, precipitation, potential evapotranspiration and temperature. Needs static maps such as land cover, soil parameters, and so on. The parameter learning component needs, well, this is where it needs any kind of data sets available that could inform the learning of this mapping between properties and the geophysical properties and the double flow parameter. But we're talking usually about digital elevation model, I don't know, for example, vegetation, canopy height, and so on. And then we need observation for the training and validation. We're using where we're using stream flow from the Alpine Drought Observatory system, soil moisture from Tuvian, and the robot aspiration. We are leveraging the special temporal asset catalog for accessing and cataloging and the data, and the OpenEO capabilities for the discovery for actually the retrieval of this data, as you can see from the few line of code at the center of the screen. Next slide. So we are building this digital twin thanks to software and computing infrastructure that different partners provide within the interTwin project. I tried to draw a diagram that shows all the resources that are relevant for DDTs, but many more are actually available that couldn't actually fit in the slide. So the yellow boxes are the component available to the end user. And the end user can access them through an OpenEO client editor, which is the one on the screen above the diagram. From this editor can access computer resources and artificial intelligence modules such as the interTwin AI and as well datasets documented and findable by Stack that are available from the data lake. So the user would start the workflow, for example, by downscaling the climate input variable, and we use the downscaling component, which is a thematic component of the interTwin project. So it will downscale the climate input variable that will be used by the model builder, which is the HydroMT software developed by Deltares to create a double flow model. It's again another software from Deltares, which is an hydrological model that will produce the output to train then the surrogate, and then again the output will be saved on Stack and will be then again read by the parameter learning application that finally then will these two applications I haven't mentioned are using the Python package that we are developing at EURAC, and as well for the computation on multi-GPU, the interTwin AI framework developed by CERN. And yes, next slide, please. So here I wanted to show a bit how it looks like the workflow. So the one on the top is the web editor. It's very small, but basically it consists of an editor, so that you can access from the browser. And each of these, we call it a process, can be linked, that are represented by these boxes can be linked together to compose a workflow. And so we'll start, for example, by loading a collection from either from Stack, basically, represented by a URL an HTTP URL, and then the following boxes would define the temporal range, the regional interest, so we reduce the amount of data at the source without need to download the whole data. And then the other application, the next one would be an application or GC application package, which is the model builder that is customizable. I don't know if you can see, it's really small, but there are some options, for example, to decide which model resolution, the river routing scheme or the overland flow scheme. And then it will this component will then produce the configuration for the double flow model. It will be run by the model runner, and finally we would save the result to Stack. Next slide. So then this is the other kind of part of the workflow. I divided in two because in one slide they couldn't fit one slide. They were not readable. So we again load the simulation from Stack. We pass it to the surrogate. Again, it can be customized by selecting a different hyperparameter. Then the next will be the performance, the parameter learning that would load other Stack collections or Stack datasets. and then we'll pass to the seasonal forecast for running the seasonal forecast hydrological variable. Next slide, the last one, I think. And here, I just wanted to show some the result from the work done on the pre-training. Here we showed that on the overall alpine region, the model showed good performance, so we can emulate very well Wflow. And yes, basically this is the last slide. Yes, thanks.
I was not supposed to show this, but Iacopo, thank you very much. That was the last presentation, and I see that we are already over time. I don't know if there are any questions from the audience. I see that Gwen also launched a survey for the people that are still here. Gwen, how do we handle the questions?
There are no questions yet.
Right, okay, so we would see.
So yeah, now's your chance. If anybody has any questions, just put them in the Q&A.
Does not seem to be the case, and that makes me think that the presentations were just super clear, which is also a fair result. Shall we still leave some time for people to fill in the survey?
Yeah, let's just keep the survey up for 2 minutes. I'll end the recording